marche.
Okay. Hi, everyone. Can you hear me well?
You can hear? Oui.
Okay. It seems like you hear me, but I can't hear you. Well, so just raise your hand and Jean-François can stop you so that you can ask questions if you need.
Yes, sure. I show you the room.
Hi.
Okay.
Jean-François, are you sure there's no way you can give me the sound so that I can hear what you say and what they say?
I try.
Actually, it was coming on the projector.
It was coming on the projector.
Oh, now I can hear you.
Yeah, now you can hear.
Okay. Okay, and the sound is good?
Yes.
Okay. Voilà. And then there is the other lab, which is appearing also by Pierre. Voilà, here is Pierre.
Well, so first I need to check if switching to the other camera to show you the setup is working. Then if I switch like this.
You hear enough? Even at the back? Okay. Because I can perhaps.
Okay. Well, so clicking here, I should be able to switch quickly. Good. Well, so first maybe I can let you have a look to the setup. So as Jean-François must have told you, we are here with the magnetic resonance setup. So this is the oscilloscope, which is not what matters here. So the device, meaning the synthesizer of the radio frequency wave that is going to excite the sample, which is here, is this one. So you have a radio frequency, which is generated inside this block at a controllable frequency, which I can adjust manually. So here we have 15 megahertz. So this block generates a radio frequency wave at 15 megahertz. And through this blue cable here, it's gonna, through this little, blue cable, sorry, it's gonna excite here inside the excitation coil, right? Into which the sample containing, an organic liquid with spins, with protons. They all have their own spin, and these spins are going to be sensitive to the magnetic field we apply. So the sample with the liquid is introduced here inside, and surrounded with the exciting, with the detection coil, sorry. And all around you have the exciting coils. So the 15 megahertz signal here is sent to the excited coils so that the spins inside the sample can feel it. And these exciting coils are going to be used to send basically the pi pulses that we want to generate to do, for example, the spin echo sequence, right? What I didn't say is here, these two blocks here that you cannot really see because they are inside, they are going to generate the static magnetic field in this direction, right? So what are we going to call the parallel light direction, right? So the spins at the thermal equilibrium, they're going to align all in this direction along the z-axis, right? The exciting coils feed it with the RF signal. They're going to generate a transverse oscillating field, right? The little alternative components that is going to create the magnetic resonance. So here is in real life, but I might show you schematics. How can I do this? Like this. So here you have a schematics of what's inside the box, right? So here is the place where you're gonna insert the liquid, the sample with the liquid inside and the protons. All around it, let's talk about first the exciting coils. So on both sides, left and right, here you have the exciting coils. So they're gonna be the ones generating the transverse oscillating B1 basically field, right? The Z field, the static field here, B0, is generated in the perpendicular direction, right? And finally, the last coil, which axis is parallel to the sample axis, is the receiver coil, the detection coil. The coil which is going to collect the free induction decay signal and send it back to the device so that it can be properly filtered, amplified, and so on. Right? So here you have another view from the side, from the top, sorry. So here the two magnet pole pieces that generates the static field. Here the place where you can introduce the sample, and here the exciting coils on the side generating the oscillating B1 RF magnetic field, right? And detection coils, which is below that you can't see from the side. Okay, so I hope it's quite clear for the setup. What we're gonna do is first generating a free induction decay signal. So sending an exciting pulse into the exciting coils, so both on the side here, so that the spins, which are initially aligned at thermal equilibrium along the direction of P0, so that the spins, under the action of the oscillating B1 pulse, they enter in resonance, and just after that they relax, right? So we're going to observe this relaxation signal, of which you know that the frequency gives, the frequency of this relaxation gives the normal frequency, gives the geomagnetic factor, and proportional also to the amplitude of the P0 field. And the amplitude of this free induction decay is going to give us the T2 star, meaning the spin relaxation time affected by the inhomogeneities of the field. We're going to talk a bit about that after. So yes, the signal we have here, I can show you again the camera here. So first, I hide the other signals. Can you see the screen well? Or is the definition enough? Okay, good. Thank you. So first, the first line here in yellow, the first signal I'm going to observe is the pulse sequence, right? So with the device, I can choose the number of pulse. So I have two options. You see, here is the pulse A, here pulse B. So I can choose sending one or two pulse, right? I can also vary the width of each of them. Here you see I'm varying the width, meaning the length of the first pulse. I can do the same, obviously, with the second one. And I can also tune the duration between them. right? So here it's fixed to 1 millisecond, but I can switch from the scale. So if I do this, up, right? I can scan the time delay between the two pulses. Okay, this is it's doable like manually with the device. So here is the pulse sequence, meaning the envelope of the B1 field, the exciting field, the shape of the alternative field that we're going to use to make the spins start the magnetic resonance. So for now, if I want to observe one single and simple pre-induction decay signal, I choose only one pulse. I choose only one pulse with quite short duration, and I'm going to observe a second signal. Second signal here, this one, which is only, so on channel 2 here, the green signal. Sorry for the quite low frequency noise that I can't remove with the filter I have, but well, I can maybe fix the signal so that it's not too difficult for our eyes to follow. So this signal is it's the reception, meaning the spin response, actually. Here you have radio frequency out, meaning it's the signal collected by the detection coil, the one you have here, right? Here, around the sample, you have a detection coil. And so when the spins inside the liquid are relaxing, this detection coil, by induction, gets some signal, and it's the one we're observing now, okay? So you see, okay, no, you don't need I mean, the first very, very high amplitude peak that you see is not due to the spin response. It's only an electronic response due to, well, internal communication in the device, so which is not relevant here. It's not physical. So the spin response is here. If I get the live start again and that I remove manually, you see here my hand. If I do this movement, like putting back and forth the sample, maybe I can show you. Sorry, I forgot to show you the sample. The focus is not that good, but still. So it's just a bit of organic liquid inside this tube. And if I do this movement, like pulling it out and in, you're gonna see on the signal that the response disappear, right? So this bump here, this green bump, is the spin response. It's the free induction decay. So I can zoom in a bit so that you can see the whole signal on the window. Okay, and I stop the acquisition so that the noise vanishes. And if I zoom in, I'm going to be able to have a look at the frequency of this oscillation, right? So I'm zooming in to the green signal. If I try to measure this frequency, so the free relaxation frequency, I can add, yes, it's already on frequency measurements. Okay, here you can see that the oscillation, the oscillation frequency which is measured is around 15 megahertz. And it's precisely the frequency on which we tuned our excitation, okay? We tune the excitation on the normal resonance frequency of the spins. And so when the spins relax, the signal they emit is at this precise Larmor frequency, right? So knowing, for example, the value of the B0 field, we could, and it's something we can do actually with this experiment, introducing here inside the setup some test limiter, a whole effect probe. We can measure the amplitude of the B0 field and deduce from the measurement of the Larmor frequency the value, for example, of the geomagnetic factor for the spins proton, right? So this is the first step. Maybe you want to have a stop here, Jean-François, now that we saw a first pre-induction decay signal. Yes. If you want to add something.
No, it's okay.
Or maybe ask questions.
Do you have any questions about that? So it's the thing that we saw during the first lecture, just exactly the scheme.
Is it clear enough? Do you get what I'm saying? Do you understand what we are seeing on the screen?
Yeah, I guess
it's
so.
Not too fast.
No, perfect.
Right.
Yeah, there's a question.
Okay.
There's a question, Leah.
There is a gap
okay.
between when the pulse is off and we are getting these oscillations. Why that gap is between the...
Okay, I'm sorry, Jean-François. I think that you're going to have to listen carefully to the question and repeating to me because I don't hear loud enough.
Sure, I will do it.
When the pulse is off,
yes.
that step function is off, we are seeing those oscillations after...
You mean why here we see that?
Yeah.
So I can answer. This is just because there is a blanking noise. In all these radio frequency signal, you have crosstalks. So there is a generator on one side, and if you look to the box, the detector and all the mixing process are just a side. So there is crosstalk. And basically what is there is just a time, and they put an electronic gate somehow that blank the signal during that window. Otherwise, it's very high. So, and then it will saturate the amplifier. So it's just a way to remove amplifier not to have saturation of amplifier due simply to crosstalk that they will see, because of course
yes. Actually,
what you have to understand is that there is often some so there are the synthesizer that produce a signal, but then this is not enough. There is a strong power amplifier that boosts the signal, and this power amplifier, it's like a radio, so it radiates everywhere. So that's why there is that.
Exactly.
Mm-hmm.
Is that the block on the device, the block which is generating the signal is here, and the one which is detecting the signal, the spin response, is this one. So actually you have some signal which is going directly from here to there, not even passing through the spin system. So the left part of the response here at very short time scale reflects that. You see that removing the spins, removing the liquid, removing the sample doesn't change anything to this early signal. This is really due to internal communication and due to the high power amplification that you have into the boxes. Just what Jean-François said. So this is not what's going to reflect our spin response here. Any other question?
No, I think that was okay. You can continue there, thanks.
Okay, so just to have a look here at the time scale, you can see here that we have 50 microseconds by division here by square, so meaning that the characteristic decay time here of the amplitude is about, let's say, 200 microseconds, right? So 200 microseconds is our T2 star, is the relaxation time, the characteristic time of our free induction decay. And it is so short. Why is it so short? Because it is affected by the the fact that the B0 field, the B0 static field here, generated by the two poled pieces, is not perfectly homogeneous at the sample scale. So all the spins contained inside the sample, they don't see the same magnetic field. So they don't rotate. The precession they do is not at the same frequency, the very same normal frequency. So they are the dephasing, the decay of the amplitude that we see of the whole magnetization of the sample decays very quickly. It decreases very quickly because of this inhomogeneity phenomenon, right? So I was going to directly dive into the spin echo sequence, but maybe before that, Jean-François, you want me to show the Ramsey?
Yes, the Ramsey is good. Yes, if we can look at the Ramsey fridge, that's perfect.
Okay, sorry. So this is not a measurement that I did today, but I can show you the principle. So going back to the situation where we have all our signal, and I'm going to say a word about each of them. Okay. So I told you that here in yellow at the top of the screen you have the the pulse sequence, so I can manage it as I want, duration, time delay, and so on. In green here you have the spin response, the Roth spin response. So it's just amplified, but no other manipulation on the signal. It's as you see it here. A third signal that I can observe and that is interesting is the spin response, which is mixed with the oscillating exciting signal, right? And moving the frequency, as a consequence, moving the frequency of the exciting signals makes some beating here appear, right? And this beat phenomenon disappear when I'm perfectly resonance, okay? Meaning when my oscillating signals, the 15 megahertz exciting wave is perfectly at the normal frequency of the free induction decay. Then mixing these both signals.
What happened? There's a problem with Zoom. It's the connection. Zoom has a problem. Ça revient.
Yeah.
Sorry, Léa, there was a Zoom. I don't know, maybe the internet connection got loose at one point.
Okay. Okay, well, I was just saying a word about the different types of signals I can observe here. But what you have to remember is that for the further manipulations, T1, T2 measurements, and showing you the Ramsey fringes, I'm not gonna look directly at the spin response, but I'm gonna look at the pink signal here, which is just a filtered version of the green signal, okay? It detects the amplitude only. So I can banish the green and blue signals, and to know the amplitude and the duration of the spin response, and I'm gonna now only trust the pink signal, which is only the amplitude of the free induction decay.
So it's basically the envelope of the signal that we saw.
The envelope, exactly. It's the envelope of the signal. Okay, so if I want to observe Ramsey fringes, I need to do a sequence of 2 high-half pulses. You have seen that, right?
Yes.
Jean-François?
Yes.
Okay.
So one pilot of 2 pulses and another pilot of 2 pulses.
Absolutely. And when we do a pi-half pulse, we want to have a maximum answer, a maximum response here of the spins, right? Because here the detection coils, which generates this induction signal proportional to the spin response, they are sensitive to the transverse response of the field, the transverse rotation, precession of the spins, right? So when you do a pi-half pulse, so equivalent in terms of block sphere to send your block vector on the equatorial plane, right? You have a maximum of response when you have a pi-half pulse, meaning that I can tune the duration of my pulse. Initially, when the duration is minimum, I have a minimum response. All the spins, or most of them, are still in the lower energy states, meaning parallel to the B0 static field, right? If I start to increase the duration, maybe you can, it's hard to see because the pulse is very, very short, but here I'm changing, I'm tuning the duration of the exciting pulse, okay? And if I want it to be a pi-half pulse, I have to wait for the spin response to be maximum. And they seem to be a bit of saturation. I can lower the gain a little bit. Okay. Okay, so I'm tuning the width of my pulse to get a pi-half pulse. So now I have a first pi-half pulse, and I can add a second one here at controllable delay time, okay? If I wanted, for example, here, they are 1 millisecond far from each other, right? And I can tune when the second pulse is alone, again, its duration, so that I get another pi-half pulse, right? So here again, I'm looking for the pulse duration, which makes the spin response maximum. When I have it, I put my two signals together, and I can measure the amplitude of the second pulse as a function, for example, of the duration of I can scan. I can remove the cursor here, which is annoying. I can scan the time delay between the pulse, but if I want, I can scan as well the frequency of the pulses, right? Of the two pulses of my Ramses sequence. So this I did previously, and I can show you the results. Doing so, you get some signal like that. Can you see well?
It's a little bit hard. Yes, we see. I can show. Okay. I can show. So basically, this starts.
I'm scanning. You see, there is some persistence to show you all the points I did. So scanning the duration, the time delay between the two pi-half pulses, I observe an oscillation in the amplitude of the spin response, right? This is due to the fact that according to the Ramsey formula, you at fixed detuning, if you vary the time delay, you're gonna observe such oscillations, right? Measuring the frequency of these oscillations could get us to the detuning, could give us the normal frequency in the end, right?
So basically, this is a measurement where we are in the situation. If you remember what we described, there is we start from this, for instance, and there is a strong, large detuning. So effective magnetic field is just a little bit, and then the spin, the precession of the effective block vector is doing something small, and so we have this kind of resonance of signal, and at the same time there is a decay by the T2 star. That's what happened.
And yeah, in exactly the same as before. So well, I did this measurement a few days earlier. So basically, the T2 star that you observe here is short. Is about 50 milliseconds. Is about no, yeah. Here you have the T2 not star. Sorry. You made the distinction, right, Jean-François, between the T2 star, which is affected by the inhomogeneity, and the T2, which is not.
No, this is T2 star. Okay, continue there. Continue.
Okay. But the T2 star is the one. I'm sorry, I never know which is
T2 star is,
and the T2 star is the one with the inhomogeneity, right? Is the one which we see here.
Yes, exactly. This is a T2 star that takes into account the homogeneous magnetic field, and then we will increase to T2 during the spin echo.
Okay, definitely. So the one with the star is the one with the homogeneity. I must remember it. Sorry. So so if we want to measure this, so the T2 star, we got a first let's say estimation of it. We got to say with the pre-induction decay curve that it was around, let's say, 200 microseconds. So it's very short, and removing the influence of the inhomogeneity thanks to a spin echo sequence, we're going to see that it lengthened a lot, the T2. So the spin echo sequence, I put it back here, but you must have saw it first with Jean-François. First, you apply a pi-half pulse to your spins, then you wait a bit, controllable tau duration. You apply a pi pulse, and this pi pulse is going to reverse, in some sense, the direction in which the phase accumulate, right? So spins which were rotating faster than the other are gonna the block vector is going to be reflected through the equatorial plane and are going to rotate the other way around, meaning that what was a phase advance before the pi pulse become a phase delay after the pi pulse, right? So so for the spins, you have another bump, tau again later, so 2 tau from the start, which reflects the fact that the spins get all together in phase again. The amplitude then of this echo of this second bump can be measured as a function of the duration between the pulse, and we expect some decreasing curve like this of characteristic time T2 this time. So T2 with no effect of the homogeneity of B0, right? So this is something that I can do experimentally as well. I can show you with the camera again. So here I'm in a situation, remind you that we have a pi-half pulse here and a second pi-half pulse here. So I must change this one to a pi pulse. So if I switch it off, changing the second pulse to a pi pulse means go to a point where the signal is minimum. Because when you have a pi pulse, we have no transverse magnetization, right? So the signal we get must be minimum. You see that you don't really manage to cancel it perfectly because of imperfections of the setup, right? But still here we have a quite good pi pulse. I switch on the pi-half pulse again, and you see, it's freezing. It's frozen to the camera for me. Is it the same for you?
Let me see, yes, the camera is frozen, yes, I don't know why.
Yeah.
No, no, so okay. Maybe you know the internet connection, so just continue.
It's back.
It starts again.
Right?
Yes.
So what you see here is the response to the first half pulse, and then 2 tau later, the spin echo signal, right? And so I can vary now the delay between the pulse, and I can see, changing a bit the time scale, and also the Y scale.
Now you see, but it's becoming very weak. You can see.
So here, if I start to vary the time delay between the 2 pulses, the pi half at the beginning and the pi pulse at the second, and the amplitude of the echo is clearly decreasing. Yeah? And so this I can do with the persistence, and I get the curve that you see here. The amplitude of the echo describes a decreasing curve like this, and this time the characteristic decay time, relaxation time, is rather 15 milliseconds, something like that, right? So way longer than the T2 star 200 microseconds that we observed previously, right? So this is how we get a T2, which is only reflecting the interactions spin, the spin between them, right? Because changing the direction of the z component of the block vector, thanks to the pi pulse, can make the phase delay due to inhomogeneity cancel itself before and after the pulse. Right? Are there any questions about that? Or we can maybe switch to the last step, which is the T1 measurement?
I don't know if there is any question. No. Yes, please.
In the last setup where she was showing about the pi poles and the corresponding emission, there was a small bump corresponding to the pi poles.
Ah, ok. Si tu peux remettre peut-être avant, Léa.
I didn't hear the question.
No,
so
the question was the small bump. The small bumps is the imperfection of the system. We cannot.
The small bump in the middle here.
Yes, yes.
Right?
Yes. No, before, I guess. It's before. The slide before. No, when you were showing the signal in real time.
Okay.
The echo signal in real time. Yes. You mean
when I was adjusting the pulse length?
Yes, I guess basically it's crosstalk again. It's just the influence of the pulse, which is checking everything and basically clack, because it's very short. So there's nothing to do with the spin by itself.
You mean during this, right? When I was trying to minimize this, and that I'm not able to do it.
And you do it at your best. So somehow there's still some spin excitation that you can.
Yeah, actually can be due as well to the fact that with time, the magnetic field inside the sample can vary with temperature slowly, and that the frequency here I send to the spin, the excitation pulse V1, is not really resonant anymore. So probably that's slightly changing the frequency could allow me to cancel the pulse a bit better. But well, you also have
and I'm sure that also the microwave excitation hits a little bit, and or the radio frequency, there's a lot of power, so maybe it heats up the coil and just the full system, and it changes a little bit. Everything is temperature dependent. So I mean, this is a demo experiment. This is just it's a system dedicated for teaching purpose. So, I mean, we do as it is. But it's already nice because you really had hands-on on the system and you can play and observe what you hear in the lectures. Yes, please.
When we are changing the pulse width, then the total decay time is more or less same, but the amplitude is changing.
Again, you have to repeat it louder for me, Jean-François.
I'm not sure I understood the question, sorry.
When we are changing the pulse width, so the total decay time is more or less same.
You mean the decay time of the free oscillation?
Time,
yes, yes.
Only the amplitude is changing.
It's changing, yes, yes.
So the total decay time will not change.
No, because it's a T2 star, so you cannot change it at that point. On each, if we could see it without the, perhaps maybe you should know, because otherwise it's quite difficult. There would be very lot of oscillations here, and so that's why we prefer to see only the envelope. But basically here, the decay that we have here is it's the T2 star, so you see it's very short. So there is a factor about here and here. There is a huge factor of difference. It's more than 10 times longer for the T2 compared to the T2 star. That means that certainly the magnetic field is not very homogeneous. Again, it's a demo system, so they made so something like now, if you purchase a true NMR system, the core of the NMR system is of course to have a magnetic field DC that is as homogeneous as you can. And now people, I think they realize things which is at the ppm part per million in the volume of your sample. So it's remarkable. The design of this NMR system, it's remarkable. And usually it's not done with permanent magnet. It's done using, of course, electro system with external coils and big magnetic materials to concentrate the magnetic flux. So this is an art by itself, designing the coil, the magnet for the NMR. Yes. But then somehow you can, from the T2 and the difference, you can see somehow you can evaluate the homogeneity of the magnetic field, which is about 1%. The 1%, it's a ratio between the two, somehow. That is somehow indicating the homogeneity of the magnetic field. Voilà. So maybe we go for the last part, or we can go for the T1, Leah?
Yeah, well, when we starting from here, it's quite quick, since here, recall, we have two pi-half pulses. The first one is a pi-half pulse, and the second one is a pi pulse, so that it makes a spin echo sequence. And now we want to switch to a T1 measurement. And for the T1 measurement, again, you talked about that during the lecture, Jean-François?
Not much, no. This you can take a little bit of time to explain it.
Okay. So here, the T1, the T1 that I want to measure is a bit different. It characterizes something way different of our liquid. We call it the lattice spin relaxation time. By contrast with the spin relaxation time, which is the name given to the T2, right? The spin lattice relaxation time, it reflects the strength of the spins with their environment and the speed with which the spins are gonna go back to the thermal equilibrium, right? Once excited, for example, with a pi pulse, so block vector points towards the south pole of the block sphere, right? So you apply a pi pulse, So what you do basically is bringing the whole population of your lower energy states in the upper energy states, right? And the one which is anti-parallel to the B0 field. So after that, here at the end of the pipels, the spins are pointing in an parallel direction with respect to the magnetic field. Okay, they're anti-parallel, so the energy is maximum. And at the end of the pipels, when B1 field stops, the spins start to relax. Okay, so they start to go back downstairs at the thermal equilibrium. Okay, they start to go back to the lower energy states, and this is done at with a certain characteristic time, and this one we want to measure.
And this one
and
would
so
be the
how,
T1 time.
Sorry?
No, I said this one would be the T1 time, the time to
Exactly.
return to thermal
This one will be the T1 time. It's the time needed for the spins to go back from the upper excited states to the lower ground states in presence of the B0 field. So to measure this, we're going to first apply a pie pulse. So tilting, switching, all the spins in the anti-parallel direction, and wait. We're going to wait again a duration, and we can vary this duration, wait longer and longer, and once we waited to detect the spin response, and here is the trick. I already said that our detection coils, if you remember the schemes in the first slide, our detection coils, this one, the one which is here around the sample itself, is only sensitive to transverse oscillation, right? Because B0 here is the Z direction is perpendicular. So with such a coil, we can only detect transverse oscillation, meaning that we don't really, this setup is not directly sensitive to Z components of the magnetic field. So if we want to observe the reappearing of Z components, because this is what's going to happen since the spins have been switched down and they're going to progressively align back all to align this with B0. And this return to the aligned situation makes the global magnetization grow progressively in the Z direction. But we're not sensitive to, our setup is not sensitive to a field growing in the Z direction. So what we do basically is applying one last pi-half pulse so that what happens in the equator plane gets back. So that what happens to the Z direction, so the magnetization growing progressively in the Z direction as the spins go down back to the thermal equilibrium, this grow in the Z direction. Thanks to the second pi-half pulse, here we project it into the equator plane, and this we are sensitive to. Okay, so this pi-half pulse here is just an imaging pulse. It's going to give a spin response, which amplitude is proportional to the value of the Z magnetization of the sample at a given duration, right? So what we expect is a response which is a Z magnetization which is starting here. It's MZ, It's the magnetization of the spin ensemble along the Z direction, along the one which is parallel to B0. At the end of the pi pulse, after the pi pulse, so actually it's more there in terms of time, but still. We expect them to be all in the spin down states. So progressively we wait and they come back to the thermal equilibriums into the ground states. So that at the end I get a magnetization which is parallel back to B0. So, right?
Mm-hmm. Maybe if I say regarding what we said during the lectures, in all these systems, in this system, T1, it's the measurement of the difference, signal. You measure the difference of population between the two levels, depending on the splitting induced by the DC magnetic field. Now, we do not have access to this measurement. For the NV center, that would be simply the level of luminescence, which is proportional to that. But here, we do not have access to that. So what we need to do is to transform this difference of population that I want to measure into a magnetization that I can detect with a coil, with a pickup coil. And this is done by just simply applying a pi over 2 pulse. So pi over 2 pulse is a way to convert things. In the other way, for the NV, it would be just the opposite. If I want to do any measurement, I have to apply somehow a pi pulse at some point, because then I transfer the dipole, the magnetic dipole information, into a difference of population. And then I can have a signal which will be the difference of intensity of luminescence that will provide me a measurement, a signal which is proportional to the difference of population. It's just the way around somehow that we will see with the NV.
Well, okay. So switching to the live camera, what I can do as a last step is taking these two pulses, switching the first one to a pi pulse, to a pi 1. So
pi pulse.
Pi pulse, yeah. If I get its duration to be minimum, I can then increase it to reach the pi half pulse first, maximum signal, and if I continue after that, I reduce the signal to get a pi pulse. So I have my first pulse, which is a pi pulse. I can add the second one, and the second one, I want it to be a pi half pulse. So I switch, I vary its duration to get a maximum signal. Right, and now again, I can vary the duration. So I start from here, and I vary the duration between my two pulses, and you see that the amplitude of, the response to the imaging pulse, the pi half pulse, which converts the Z magnetization into transverse magnetization, into detectable magnetization, its amplitude decreases with time, and it decreases until it reaches a minimum, and it starts to grow again. It starts to grow again, just as we have here on the curve. On the data I took for you here. Well, first we have a decrease of the amplitude of the spin response, and then an increase. And it's exactly the curve we expect. The first part, the negative part, is obviously positive in our setup. We are detecting a transverse field, so a radial component in the outer plane of the Planck sphere, we only have a positive value for that. So it's equivalent taking the absolute value of the negative part of the signal. So here what we see is an exponential growth of the Z magnetization. And spotting here the value, the time value on which the signal crosses the zero axis gives us the value of T1 times the log of 2. So if you see the value here, you have something like 15 milliseconds. You have 15 milliseconds here. So dividing this by log of 2, you obtain a T1, which is approximately 20 milliseconds, right? So which is slightly higher than the T2, but same order of magnitude. But I think it's something quite frequent, quite common, right, Jean-François, that the T1 is longer than the thermal equilibrium relaxation time is longer than the spin-spin interaction relaxation time.
Yes, it's longer. The limit would be T2 equal to T1, but in practice the T2 is limited by the spin-spin interaction and doesn't reach that. Maximum value you can get for a T2, for a two-level system, is two times T1. It's what we have, for instance, for spontaneous emission of an atom. For those systems that are in condensed matter, the spin-spin interaction that somehow set the limit for the
T2 from going so high, right?
Is decreasing the T2 comparing to this limit. And we have what we wanted to show you is that we indeed have T1, T2 star, much smaller than T2, and T2 is smaller than T1, and it's what we observed here, what we measure. And we wanted really to show you that. Good? Okay, thanks a lot, Léa, bravo. Huh?
No worries. Well, if you have any question, but maybe we're going to switch to Pierre experiment because you've gone a bit of time now.
So thanks a lot.
Well, no worries.
Thank you very much. And I think let us give her a very big applause for
Thank you. Well, I just leave the meeting. It's not gonna. No, yeah, it's your meeting, so good.
Okay, so we switch to Pierre now. So
bye.
Thanks, Léa. Thanks again.
Bye, Pierre. See you later.
Okay, Pierre, do you want me to? Do you want to show or I can do it to show?
The easiest is I will share the screen from Gyro NV, so the lab computer, and you can also see me live on my personal webcam. Yeah.
Okay, good, very good. And then I've not. Do you want me first to share the detail of the experiment and we reapply, or you will do it online?
Where did you stop? What did you explain until now?
I can show you.
I think I can do a lot of things by myself.
I'm sure.
I think.
Let me see.
I have my PowerPoint. I can show the one I gave you.
Okay. Then I can show you what we did.
Maybe we can go back and forth if you want something. Okay.
Let me see. Pouf. This is Keynote. Okay, partager. Voilà. You should see that. Okay. So I'm not putting full screen. It's not the purpose. But basically, what we have done is explaining this signal this morning, and I explained that also those signals that we see now really just we can perform nuclear spin optically detected magnetic resonance on nuclear spin. the same way as we do on the electronic spin of the NV, just by measuring the intensity of luminescence of the NV center. So the NV center is a kind of ancilla of the nuclear spin manipulation. Okay? And
okay.
so
yeah,
everything is done. And
I
then
will go through this.
What I didn't explain the experimental setup. I can show it, and then you can explain it, or as you want.
I will do everything. Don't worry.
Okay.
I will do the presentation.
Okay, so then I close mine, I stop sharing, and you can do it.
Okay, so I need to share you this screen.
Maybe you need to ask me if for sharing, sorry, you need maybe...
I think it's good.
Okay, it's good.
Okay, okay. So first of all, let me show you, so you've seen that with Jean-François. We are using NV centers inside of the diamond lattice. We also call, well, NV centers are one of several color defects, color centers, and that I can really show you. So here is the camera. You can see the diamonds we are using. So as you can see, you have here two diamonds coming from the same manufacturer, and between them you have, this one is something like 10 times less dense in terms of NV centers than this one. And as you can see, NV center diamonds are really, really pink.
So you have here the concentration. So the concentration is 300 parts per billion. So basically, it's barely transparent. You don't see anything. And those are highly doped, 4 ppm, and they are really, there's this nice pink color, which is specific of the NV centers when it's highly concentrated. Okay?
So this part per billion is in volume?
It's in volume. All the samples we will show are really done in volume. The other one that we produce for the other project of that we're working on are created. It's more like a thin layer of NV that will have something like 10 nanometer width and a local concentration of about typically 1,000 NV per square micrometer. So it's more like a 2D layer of NV. Those are really for building magnetometer. You want to have as many NV as you can. So that's why we use NV doped, strongly doped samples. Sorry. Yes, please, Pierre. Pierre? No? Oui. Pierre, ton micro? Pierre, we don't hear you.
Yeah, sorry. I wanted to try to use the microphone from the moving webcam. So, yeah, as Jean-François told you, I'm going to show you one experiment with the way we use NV centers to measure, in this case, rotation to make a gyroscope. Okay? So, this is the experiment in its integrity. As you can see, we have, so optical stage, you have I will just
Pierre, on n'entend pas. Ouais, vas-y. Ouais.
It's okay? Jean-François, do you hear me?
Faut pas aller trop vite, je sais pas, il se perd après. Vas-y, va doucement.
Super, ok.
Ah, on a perdu. I think it's gonna, yeah, it starts again.
Maybe I can show you up close the diamond itself.
Oui, voilà.
So the end result is this. Let me try to make it a bit more clear.
So that's the art of the experiment. Really, the heart of the experiment is there. So basically, it's what I explained today, this morning. What we want to do is apply a magnetic field that will allow us to transfer the NV polarization, electron spin, to the nuclear spin polarization of the nitrogen-14 that is intrinsic to the NV center. And this is done by applying this strong magnetic field at around 500 Gauss and align it on the direction of one NV family. We work with, again, 100 sample, so we have 4 families of NVs, and that's why you have it on this axis, because the magnetic field is aligned along one of those families which are distributed with different angles. In that case, it's about 37 degrees compared to the axis of the sample.
Exactly. So this I will show you with the ODMR later. So what you can see here on the picture is antennas. We have 2 RF antennas here. Okay. This is an electromagnet that we can orient in both directions, and the diamond itself is in the center of the picture, and you can faintly see the fluorescence light, but let me show you what happens when I what I see when I have the glasses that are blocking the green laser. Here the light you can see is only due to fluorescence, to orange fluorescence from the diamond. Okay? So this fluorescence is what we'll use as a signal, and down here you cannot see much, but this is the photodiode. This is the sensor we use to measure this photoluminescence. Okay, so now let me show you what happens when we send by using all of this instrumentation. We have here an RF synthesizer and amplifier, okay, that goes, if you follow this, that goes to the antenna. So let me show you what happens when we sweep RF frequency in this antenna. So I just have a little bit of preparation to do. Okay. Okay. So when I press play, we should see. I have to check a few things. Okay. Okay. We should see something appear on the screen in a few seconds. Okay, there we are. Okay, so what we see here, it's not very clear because you'll see the setup. The antenna is not optimal for microwave. So we are sending microwave. You have here the frequency, and we can see 2 things. Here, something very clear with 3 peaks, and here, less clear. We have only 1 blob. Okay, let me show you what happened when I change the magnetic field, when I change the orientation of the magnetic field. Okay, so I will do exactly the same scan. But now the magnet has moved. Okay, we can't see much now in this configuration, so we'll have to do some averaging. So if you understand what we are seeing, if you understand what Jean-François has explained to you, what we see here is on the left, one NV family, and on the right, which is not very clear at the moment, but we should see, you can see maybe better here, we have in fact 3 other NV families, okay? So first thing I have to do is to align properly one family with the magnetic field. So one way to do it is to superpose those 3 families. Okay. So when I change the magnetic field back, okay. I just got back to the first configuration you saw, and now all the 3 families we had before on the right are now merged into only one signal, okay? And the one you can see here, the one that's alone, that's aligned with the field, so it's seeing the highest field, it's moved to the left, okay? Because it's seeing the most magnetic field it can see. Now, next thing I need to do, I'm quite sure I'm well aligned with the field. Yes, Jean-François?
Just to say, so if we take back what we said this morning, this is ms equals 0, and for the moment, and ms equal plus 1, 0, mi, sorry, and minus 1, okay?
Mi, yeah.
So mi, so we have the 3 components associated to the 3 values, the 3 projection of the nuclear spin along the z-axis that is defined like that. That is defined
exactly.
by that. And then
what we see here on the left is for only one family, those 3 transitions.
Exactly. And all these are somehow optically linked. You link this one to this one, and remember, all the link that is done will not change delta mi. At delta mi up to now, we are not are completely decoupled. Is decoupled up to from ms. So we everything is done by conserving the projection of the nuclear spin.
Exactly. So now what I will do, we need a way. If we want to do nuclear spin manipulation, we need to polarize the sample. So as you can see at the moment, I have NV population is equally distributed between the 3 MI level, the 3 hyperfine levels. Okay, so I need a way to polarize the system, and this is where maybe you stop with Jean-François.
No, I explained that.
You explained it? Okay. So now we are going to go to the SLAC. Okay. We are going to apply a stronger magnetic field around 500 Gauss. And this will get rid of 2 of those resonance. So let me show you. I need to change, since I'm going to apply a stronger magnetic field, I need to go further down in terms of, so this family is going to go left. It's going to leave the string. So I need to go where I know it's going to end up.
Of course, there's a Zeeman effect. So as soon as we increase the magnetic field, it affects. And with the nice thing with the magnet that Pierre designed, it's an electromagnet, as he said. So this was designed by him. And the good point is that you can easily tune the value of the magnetic field just by the current through the coil. So exactly. we can easily do that. With other experiment we did, and I showed you the result, it was a permanent magnet, and that was a lot of, that ended in many problems, because of course it was very easy to do, it was easy to implement somehow, but the problem is that tuning them was rather difficult. So all these operations took almost a day of adjustment, whereas here you see it's a few minutes of work due to this design. And of course it's rather bulky, but nevertheless the system was designed in a way so that we can return the magnet and optimize the angle of the magnet to have the alignment along the family with this rotation.
Exactly. So at the moment, the signal you see, we are at lower frequency, but I didn't change the magnetic field yet. So as you can see, we have nothing. We have nothing to show here. I have here, I have to show you the camera. Okay. Here I have a power supply that I use to change the current going through this huge coil, the huge copper coil here. Okay, and this will change the the magnetic field. So I will do that live, and you'll see what happens. Okay, let me just. See. Okay. So here I just have to change. The problem was that the photodiode was in saturation. Now we should see something. No. Okay. So I guess my alignment is not good. Sorry, sometimes it can be a bit tricky to find the resonance, and you'll understand why in a moment. Okay, now we can see something. Okay, I can do this.
So now we have somehow, thanks to the magnetic field, all the nuclear spins are polarized into Mi, into these coupled states between the different the two states. So we have polarized all the nuclear spin into ms equal -1, mi equal -1, for instance. Using the process that I explained of this of this flip-flop transition between at the S-slack.
Exactly. So now, as you can see, I am at 1.6 gigahertz compared to 1.7 before, the 2.7 before. So we are much higher. The Zeeman effect is much stronger because we are at higher B fields. And as you can see, we only have one resonance now. So we got rid of two of the hyperfine resonance. Now, let me show you the importance, and I need to do it before we go to the next part. I will show you what happens when you change the when you change the orientation of the B field. So, okay, so I just zoomed on this resonance to have a fast update, and I will change the orientation of the magnetic field. So this is a bad alignment, and I only moved by something like 1 degree. And as you can see, I almost killed the resonance. Now I need to find the optimum setting. Okay, went too far. To go back. Okay, so this is for one axis, and the other, let's see. Okay, so I think we already were at an optimum.
Yes, it was not bad.
Okay, so now I have the right magnetic field and the right orientation. So the right intensity and the right orientation, we are in the right condition for the S-lag. We are in those conditions, okay? So we see only one peak, one resonance. We see this, because now we are mixing the MS and MI spins, nuclear and electronic spins, in such a way that we are polarizing the setup, the diamond, into the MS equals 0, MI equal +1 state. Okay, this one. Now, this means that we have a 3-level system. We can use directly the 3-level system. That's the hyperfine structure of the MS equal 0 MS equals 0 state, okay? So we are only using this part of the NV structure. And I can show you that by directly addressing the NV nuclear, the N14 nuclear spin, using not gigahertz, but megahertz frequencies.
Around
okay?
5 megahertz. Now we can really drive, we can forgive somehow the NV. The NV are not, they are just for the optical polarization, and we can really play, and they provide us, of course, with a signal, but we can really play now only with the radio frequency signal at 5 megahertz. So that takes a little bit of time, because Pierre needs now to change generators, because it was a microwave generator, and now it's much simpler generator with providing signal at 5 megahertz. And those signals are amplified using mini-circuit amplifier, so that we have enough power somehow to put in the antenna to drive these nuclear spins. Okay? So not anymore microwave, any microwave excitation.
Exactly, yeah.
So somehow we are back now to the situation that Léa showed you before, apart that somehow we have two main features that was not in the experiment before. We have a way really to polarize the nuclear spin. In the other experiment, we were only relying somehow on the thermal distribution, on population difference associated to the temperature and Boltzmann law. Here now the spin are really polarized, that provide huge signal compared to the other system. And also the big difference is that we have an optical readout through the NVC system. So we have a direct measurement using the NV electronic spin.
Exactly. So now what I will do is I will scan between 5.05 megahertz and 5.15 megahertz. And that I know I should find the resonance corresponding to this transition, the transition from MI equal +1 to MI equals 0. So let's see if everything works as intended. Did I do everything okay? Yeah. Okay, so no. I forgot to switch on the amplifier. Yeah. So here, you still hear me because the amplifier is very loud.
Yeah, we see.
It's okay?
Yeah, we see.
Okay. So here, this dip, you can see, is another resonance. So in the way we do the experiments, you cannot rely on the resonance can be positive or negative. It's not the problem. It's not important. So we have this resonance at 5 points, in this case 5.08, a bit more, and you will see now what happens when I change the intensity of the field. So I will just send a bit more current into the coil. So as you can see, by changing the magnetic field, I just changed this resonance. And this is due to the Zeeman splitting between Mi -1 and +1. So this difference here is splitting due to Zeeman effect. And that's what we can see here. Okay? So I can use this signal to further, no, okay. Well,
maybe Pierre, you should explain what is the resonance between the M value that we measure?
Tell me again?
Well, maybe come back to the scheme.
The scheme?
To the slide, yes. And explain, we do not observe directly Mi +1 to MS to Mi -1.
Oh, yeah. Okay, so Mi +1 to -1. Yeah, okay. So this difference from M1 to from Mi -1 and plus to Mi +1, we would expect something like 300 kilohertz. In fact, I can show you, but there's no real meaning to do it. In fact, we would not see anything because
it's 2 h-bar.
Because of selection rules.
Yes, it would require 2 h-bar of angular momentum to have this transition. And each radio frequency photon can only bring h-bar, so we have only that selection, that transition that are allowed in. This one is forbidden, okay?
Exactly, yeah, it's forbidden.
So that's why we are...
Only one photon. It's forbidden with one photon, but you'll see that yes, we can do it with 2 photons.
If we have 2 photons, then we can do it. A little bit like when in optics, when you have 1 photon transition allowed, like the 1s to p. This is a 1 photon in hydrogen atom. That is a 1 photon allowed transition. But 1s to 2s is of course forbidden, but it can nevertheless be allowed by 2 photon transition.
Give me just a second to optimize this signal.
Yes.
Oops. And then we can go to the next step. Okay. So here what I'm doing is I'm changing the orientation, because I know at this stage I have a lot of, I'm very sensitive to the orientation, and as you can see, okay, I'm good. Okay, as you can see that the signal is changing a lot when you change the orientation. Let me show you one last thing before we go to the next part. This will show you what this represents. So this we've seen, okay? One resonance for
a given magnetic field amplitude.
For a given magnetic field. Just a second. I have a strange behavior.
No, perhaps, yeah, if you want to go directly to the Ramsey fringe, it's okay.
Yeah, okay.
That's the most important. important. The other one I explained, so it's more technical.
Okay.
Unless you want to see the radio oscillation. We want maybe to see the radio oscillation first.
Exactly, yeah. So now we have a three-level system that's polarized, and we can coherently manipulate those spins inside of those three levels. So let me show you what we do first. First thing we will do is to measure the Rabi oscillation. Okay. No. Yeah. I have to change a few things in my program because everything is driven the way I'm programming this setup. So this is the sequence of pulses I will send to this device here, and this device will send those impulsions through here, and those are used to open and close switches, RF switches here, and you'll see the result on the oscilloscope that's here. Okay, so
these are pulses of microwave of the radio frequency drive at 5 megahertz, and we using a mini circuit driver, we can shape them as pulses. Okay.
Just have to change back the configuration. Okay. Okay. Here we are. So what you see here, the green trace, this one here, is what happens when we turn on and off the laser. I can show you maybe this way, okay? Here. So in fact, this is what we see here is the fluorescence in some way. This is the fluorescence. So the laser is used with NV centers. The laser is used for two things: to initialize the system, okay, and to read its state. So both this at the end of this laser pulse, the system is reinitialized, and at the beginning of this one, we read its state. Okay? Now, what we do, okay. What you see here is a Rabi oscillation.
So it's the Rabi oscillation driven by the RF signal.
Yeah. Give me just a second. It's not very good at the moment. Okay. What do I want to show? Okay, it's the same. Okay, here we are. This is better. So, what do you see here? Each point of this oscillation, each point of this graph is the result of one of these one of these sequence of calls. So if I stop the oscilloscope, this is one point of measurements. This is the result you can see in here. One point of this curve is the result of this readout, of one of those readouts. And what we do is we stay on one frequency of one RF frequency, but we turn this frequency, we turn it on for a longer and longer time, okay? So this is kind of what Leah showed you before, but here we can do it continuously. And since we are doing a destructive measurement compared to the way Leah showed you, she could show you the oscillation directly. We cannot, because when we send the laser to make the readout, we repolarize the sample, so we destroy the information. We measure it, but we destroy it too. Okay, now let me show you what happens when I change the RF amplitude. So if I go to higher RF powers, the theory predicts the Rabi oscillations, the Rabi frequency is higher, okay? And if I go to lower powers, we'll have we'll have a lower Rabi frequency. Okay, so to do coherent spin manipulation, we need to measure properly the time that's needed for a given RF power, the time that's given to reverse the polarization. So to reverse the population. So just to remind you, this Rabi oscillation tells us that at this point, the at the beginning, the population is here, and when we send the right amount of RF, we end up here, and when we are here, the population is in this state. Okay, and we need this time. We need to measure this time, and this I need to do it quickly. Okay, so I've done only one acquisition, and this is the result. And I can quickly measure the time between what we call the pulse time. Okay. Okay, and I end up with 91 microseconds. I will put that in my program. Okay, and now we can do Ramsey fringes. Okay, so let's go back to the oscilloscope. now what I'm sending to the antenna, as you can see, yeah, tell me, Jean-François.
So you have a first pi over 2 pulse, that's it? Here?
Yeah.
And then we will have a second pi over 2 pulse, and
exactly.
we will change the duration, the time interval between the two applied pi over 2, exactly like as Leah showed before.
Exactly. And as you can see, it's the pi over 2 is 45 microseconds in duration. So it's really half of the time we measured earlier. And the second one, I'm just changing its position, and this way we can plot this oscillation that corresponds to Ramsey fringes. Okay, so why do we have an oscillation? That's the result of beating between the NV natural frequency, the nuclear spin natural frequency, the Larmor frequency, and the frequency of the RF we are sending to it. Okay, so now what I need to do is to tune properly. So I have two solutions. Either I tune the RF I'm sending to the antenna, or I can tune, since I can change the magnetic field, I can tune the natural frequency of the NV. That's what I'm going to do. Okay, so you see, here I'm applying more magnetic field, and in fact, I'm increasing the detuning. So the frequency, the frequency we observe is increasing. I need it to be, I need to decrease it. So I will decrease the magnetic field until I make those oscillations disappear. Okay, this is what we obtain. So this is the kind of the envelope of our signal. This is directly it's not very clear, but here we have an exponential decay. And this exponential decay has a time of T2 star. This is T2 star decay. Okay? So, one last thing. What I'm doing now, what I'm doing now is sending, so the first pi over 2 pulse, as you can see, it begins with a given phase. In this case, it's 0. So I'm beginning the pulse with a phase of 0. And the second one, begins with a phase that's depending on where we are putting the second pulse. Okay? What I'm going to do is I'm going to reinitialize the phase so that the second pulse is looking exactly like the first one.
Because otherwise you mix up the X and Y state. So somehow you have to rephase the signal so that you are really with the same X and Y. Here we don't know. You somehow, when you apply the second pi over 2 pulse, it's like interrogating, but again with a random phase regarding the first one. So that's why we mix up the signals somehow. But then if we restart with the other one, we're sure that somehow we restart with the same phase. It's a little bit a subtle point.
Yeah. So in the Bloch sphere, in the previous experiment, the X and Y axis were rotating at the same time as the spin inside of the sphere, okay? So we had to take into account the combination between the two rotations. Now, I'm fixing the second, by fixing the second phase, I am fixing those X and Y axes. And the result is that now we cannot see a beating. We don't see a beating. We directly see this oscillation is directly the Larmor frequency. So now the only way I can change this frequency is by changing the B field. This frequency won't change if I touch the RF sensing. It can disappear. If I go too far, it can disappear, this oscillation, but it cannot, I cannot change its frequency. Okay? Don't hesitate to interrupt me if you have questions.
Maybe if you can show the decay of the signal or not, it's too...
Yeah, that's what I'm trying to do, but it's so long. The problem is that when you do this measurement, you need to have a measurement step that's very narrow.
Sure.
And so you do a lot of points, a lot of measurement points until you can see really a decay. But if we wait a few minutes, you should see a decay. And this decay is the T2 star decay, so the decoherence.
And the T2 star will be in the millisecond range.
Exactly.
It takes time. Yes, please.
The units of time here and scaling.
Yes. I mean, it's just the way the signal appears. So basically, we're just restoring what's happening is that somehow. Not sure I really understand your question.
The time scaling unit, is it in seconds, microseconds, milliseconds?
Ah non, this is in... La question, Pierre, c'est en quelle... What is a unity? It's a second, microsecond, millisecond?
Okay. So what you see here on the screen, you cannot rely on the scale down, the X and Y scale. So the Y scale is in fact the voltage on the photodiode. So it's
on this direction, yes.
You would need, yeah, the Y scale, this one. You would need to transform it to really have an idea of the contrast of your photoluminescence.
The question was more on the X axis.
Yeah, the X scale, the problem is that it's a combination between the way I program. So maybe I can show you with the oscilloscope. Okay.
It's better with the oscilloscope.
This pattern, so it's slowly moving now. You can see this one is slowly moving.
We need to integrate.
Yeah, and you have to take into account that this, so one of those is 1 point of measurements, and I'm repeating this a certain amount of time per second. Okay, so you need both information. You need the width between two measurement points, the delay between two measurement points. I mean, this delay between this point and the next, okay, and the sampling rate. You need both information to be able to understand
what is the time actually in the system, because of course you repeat. You do one scan, you shift a little bit to repeat, you shift a little bit to repeat, because of course the signal over background will depend on the integration of all signals. But you see already the decay now, okay? That starts to appear. So this is really, after a while, now we apply the pi over 2 pulse, the second pi over 2 pulse, long enough so that we're starting to see the influence of the T2 of the D2 star on the nuclear spin. And what you want to do, and somehow in any practical measurement that I would like to do, for instance, that would shift. Pierre will make a demo, I guess, at one point. We will see at one point at the end. Of course, what you want to have is to see, for instance, the influence of an external parameter. And to get the influence of an external parameter, in that we will all these experiments, for instance, if we apply an external magnetic field, the external magnetic field will create a dephasing. Okay? And of course, the dephasing will be simply mu times b times the time of measurement. And you want to have the longer time, the longer duration you can for your measurement. And the longest duration that is allowed for the measurement will be set by the T2 star. And after that, of course, we have completely lost all coherent process, so we cannot see the influence of the magnetic field. If we put a very tiny magnetic field, external magnetic field, that will progressively shift the fringes. Okay? And of course, to see the largest shift we can, we need to wait. And we can wait up to a given limit, which will be set by the T2 star. Okay? And so at one point, Pierre might stop.
I will show you. This is the next step. The next step is exactly what you are explaining, Jean-François.
And then somehow we could compare, and then Pierre will bring a small magnet, and you will see that the coil, the fringes will change, and of course the fringes that will change here will change larger than if we have done it from the very beginning. Okay.
Exactly. So. You understood the decay, and the frequency of this oscillation is this corresponds to 1 megahertz oscillation, okay? But you cannot rely on the time scale. Okay, so now which is this one between the two levels MI minus 1 and plus 1. As I told you, it's not possible to do that with only one RF photon, so we need to use two of them.
You want to see the double contact?
Yeah, I'm going to show the double contact. So we've done this, okay? I've shown you the difference between using synchronization and not using synchronization on the RF phase. And now we are going to do this, okay? We want to do this sequence.
Yes. So it's a sequence where we apply 2 microwave fields. And by applying a microwave field, 2 microwave fields, somehow, suppose you have the influence is that if there is any drift of the parameter, the drift will affect the two parameters the same way. Okay? So somehow, compared to this one, which is mostly insensitive to anything. So if we now look at the transition between that, will be now in the 300 kilohertz range, or even less, sorry, then we can really have a much more sensitive experiment because we get rid of a lot of imperfection.
And let me explain to you what we are doing. So those are the pulses I will send. So those are the pulses of RF pulses we are using. This one, the green one, corresponds to the the plus 1 to 0 transition, so the long one. And here the purple one corresponds to the short one, okay? And first I need, before we can do the Ramsey oscillation, the Ramsey fringes, we need to project the population. So after the laser pulse, the population is in this state, the plus 1 state. So to be able to do this sequence, we need to first project everything on the 0 state. That's why we are using first, here this is a pi pulse, and then we can measure, I will show you the oscillation we can see. And in the end, we do exactly the same thing. We project back everything that's here. We project it here, which is the most fluorescent level. Yeah, exactly.
Just sequence of pulses that are applied, and that's somehow the strength of those signal, that you can really play with the state just by this combination of pulse and time. That's what we wanted also to show. And basically, all this spin-based physics is just using that. But it's amazingly robust.
So, as I told you, here, on the left, we have the pi pulse of RF1, the long RF, the high frequency, the higher frequency, okay? And this is pi over, it's not pi over 2, in this case, it's pi over square root of 2, okay? But it's the same principle. But this is pi over 2 pulse using both RF frequencies. So we have, since they just superpose in the antenna, we have a bitting between them, okay? So this is the result. What you see here is the result of additioning RF1 and RF2. And as before, we are slowly moving, the second one is slowly moving to the left, okay? Now, what do we see now? We have this oscillation.
This is real time.
Yeah, this is real time. This oscillation, so I will stop and explain a bit. The low frequency oscillation, this one, this corresponds to what we need, what we want. And what we want is here, this transition, okay, the blue one.
So it's a coherent drive.
Here, we put the system with the first pi over 2 pulse, we put the system in a superposition state between -1 and +1, and what we see is the oscillation of population between the two, so the Larmor frequency. Now, the faster oscillation, this is a 5 megahertz oscillation, and it's a remain, so it's a sign that the setup is not correctly set, because this should disappear, okay? But it's the remain of those higher frequency transition, okay? So for us, we need to get rid of it, but I don't have time to do the settings properly, but we would need to get rid of it, okay? The important oscillation for us is the low frequency one, and that's 300 kilohertz. Once again, you cannot rely on the time scale. Okay, so what we need to do, this would behave exactly like the previous oscillation I've shown you. We would have a long T2 star decay. And what we are going to do, we want to measure, to do sensing, to do accurate sensing of different parameters. Yeah, okay, so I can quickly sum up here. We are looking at this frequency, what we call the double quantum frequency. And this frequency depends on two parameters, the B field, okay, and the rotation rate of around the NV axis, okay? That's called nu here. And this is very fine. Nu is very fine. It's under the Hertz range. Yeah, it's under the Hertz, and the reference frequency is 300 kilohertz. We need a way to measure properly this frequency, and this is the method. Okay, so what we do is we start the oscillation at some point, and we will look at a very specific, and the further the better, a very specific free precession time. Yeah? So the output of this, I can show you. Mm-hmm. Okay. Okay. So now I'm always repeating this sequence you have here, this sequence of pulses, okay? And the second one, the second pulse is not moving anymore, okay? It's always staying at the same point. So we won't see oscillation anymore. And here you can see, well, this is noise, but if I filter a bit more, this is not oscillating. Okay? Now let me show how this is very sensitive to magnetic field. Here, I have a magnet here. Here. Okay. Here, inside I have a permanent magnet, quite strong one. And look at the signal when I move, maybe I can plot both. It would be nice. Okay. This? Okay. So let me show you what happens when I go near with the magnet. You can see this oscillation.
Just the radio fringes that somehow change the Ramsey frequency.
Exactly. So with the magnetic field, in some kind of way, we are going back and forth in this oscillation. So in the reference oscillation, okay? So we have a setup, we have a sensor that's sensitive to magnetic field. And it's also sensitive to rotation, as I can show. So at the moment, the setup is not able to rotate properly. But if I do it with my hands, you can see the output result is that we change. We have an oscillation appearing due to the oscillation of the frame.
Okay. Well,
and might think, so with this setup, we could do an echo measurement. We could do any kind of pulse sequences. But you've seen some with Léa. Jean-François, I think we can stop there. I can answer questions if you have in the room.
Yeah, that stops the demo requirement, but of course we can ask questions here or answering. Any questions on that? Maybe everyone is a bit. Yes, please.
I just have a point out that this has just 5 out of 2 pulse, not 5 out of 2. So why do you have?
Why we change the pulse? Why it's not 5/2, but something more subtle when we go to the double quantum?
This would appear when you do the calculation. When you do the calculation to put the system in a superposition of states, you would find 5/2. Square root of 2. It's for normalization reasons.
I have no. Somehow it goes as a square.
Yeah.
Change a little bit the formula. Is there any other question? Okay, so just we wanted to show you, in real time, so and you see it's not so super complicated experiment. Actually, a little bit nevertheless, but because there's a lot of effort on programming and all that, but it's quite amazing that somehow, at least for me, that we can use such demo of the system and now up to a point. So we hope now we're changing a little bit the configuration because this configuration with 100 sample, it might not be very well suited for really making an appropriate zero. So we're changing a little bit the configuration to make it more, to adapt it and changing some parameters in the crystals. And that's the system that is now planned that we're going to do, we hope, in a few months with a system that basically will be with a laser. There will be a very narrow system for the specific orientation, and we hope that all the electronics that somehow are bulky for that, we hope now to integrate that into only one replica that can provide all the information that are required, and all the signals, the locking detectors, everything, so that at the end we have a system which is as compact as possible. Okay, we'll see. Maybe next year we can bring the system here. Good.
Okay, so let us thank Professor Raj and the team for the wonderful demonstration.
Thank you, Pierre.
Thank you. With pleasure. Thank you very much.
Okay.
Yes.
So that closes a little bit the part of the lectures. Now it's your turn with the presentation that you will have to do. So I hope you enjoy these lectures, or you learned and you saw. I mean, of course, the experiment far from here, far from there, but we hope to somehow give you an idea, a flavor of the things what we are doing. There are other experiments in the team, but this one is, I think, which an amazing point of stability and reliability. With care.
Maybe he wanted to say bye and then.
Okay, bye-bye. Good. Okay. Thank you a lot.